Good morning, students.
Good morning, ma'am.
Yeah. So today there is no exam, right? Any placement exam is there today? Yes. Any placement exam is there today, students?
Yes, ma'am.
It is there today as well. What time?
Uh, one one is from I think Josh is conducting at 10 a.m. and then
Oh.
yes, ma'am.
So you people will be leaving in between, is it like that?
Yesterday first round happened, ma'am. So maybe the
Acha.
shortlisting happened.
Okay, no problem. All right. Okay. Okay, fine, students. So we will continue with what we were discussing yesterday. Okay. So we were talking about this is the algorithm for it. So the basic thing that merge sort consider is we are talking about merging algorithm, right? So first we had algorithm that we call as merge sort that is going to iteratively call itself. That was merge sort. So what it does is it first find out the length, divides the length, and then it creates two new arrays. One is called as L and another one is called as R, and then it recursively calls the merge sort. Now we have another algorithm that is called as merge. So it's like, first part you have done the division, divide, and then then you are solving the smallest subproblem L and R, and finally you are combining the solution. So the combine assume this that L and R are already sorted. Then this was the algorithm that you create a new array, right? The length of that new array is going to be the combined length of both the arrays, both the sorted arrays, and then you take the first array and then you compare it with other elements of other arrays, right? And then we had taken indexes I and j. So the same algorithm, we have made a working solution. So suppose you have these two arrays, L and R. So purposely we have taken it like this 1, 2, 5, 8 and 2, 4, 6, 7, right? And this is sorted in itself, this is sorted in itself. But now when you see 1 is less than 2, then 2 is less than 3, 3 is less than 4, like that it should come into sorted array, right? So this is our merge algorithm. So we will just have a look how it works out, right? So it starts like this. You have create array B of length L plus length R. So you have created array B of size 8, right? And then the two indexes I and J. I works here and J works here. I is 1 and j is 1, because we have already decided that we are going to take the index of array from 1. Now k is the index to work with this here, right? So for k equal to 1 to length of b, right? K equal to 1 to length of b, because we want to fill all the 8 elements in b. This is what we are checking. If j is greater than length of r. So here j is certainly not greater than length of r. Right? J is not greater than length of r, but we have put this condition so that once we have traversed completely r, we can come out. Okay, but this or condition will be true. Or I is less than equal to length of L and Li is less than equal to Rj. Right? So here I is less than equal to length of L, but we have not completed the traversing the left hand side array, and Li is less than Rj. So 1 is less than 2 here. Right? So in that case, what we are doing in BK, in B we will put Li, the smaller element, and we are going to increase the index of left hand side array by 1. We will not touch the right hand side index R. So we come here, this and this 1 is placed in B. Right? Now it will not go to L. Right? Again we make k is equal to 2. Now k becomes 2. Right? Again when k becomes 2, it comes here. First condition does not satisfy. The second condition also doesn't satisfy. Li is not less than equal to Rj. Right? C is not less than 2. So we come to else part. So Bk becomes Rj. Right? So it comes here. So the 2 is copied here and j becomes 2. Like that we are going to travel. Then again k becomes 3. Right? Now when it goes here, again now this condition satisfies. 3 is less than 4. So 3 is copied here. Next time it goes to else part. So 4 is copied here. Next time it goes to if part. So what happens? 5 is copied here. Next time it goes to else part, and then 6 is copied here. Right? After 6 has been copied, it again goes to part, right? And now I is less than equal to length of L. This condition is satisfied. Right? And Li is less than equal to Rj. This condition doesn't satisfy, so it comes to the else. Right? Now 7 is copied. Now after 7 has been copied, j has become j plus 1. Right? So now j has become, j was 4, so now j has become 5. Right? So now j is greater than length of r. Again it goes here. Right? Or I is less than equal to length of L and Li is less than Rj. It doesn't satisfy, but it goes to this part. Right? Part, and the 8 is copied here, right? After 8 has been copied, now what are the indexes? I has become 5, right? And j has also become 5, right? So now it goes here, j is less than length of r, j is greater than length of r, yes, j is greater than length of r, or, right? Now j is greater than length of r, or I is less than length of I, and Li is less than equal to length of less than equal to Rj. Right? So this is how the algorithm terminates, right? So the next question is, does the algorithm terminate? Again, to prove that the algorithm terminates, we can prove it by taking an example. And then you can always say that if there are 8 elements, if this is how it terminates, so you can always prove it by the method of induction. Right? Does the algorithm terminate? Is it correct? Yes, it is correct. Okay, again, how it is correct? So to prove the correctness, we again can take an example and prove it by induction. Otherwise, we have the concept of loop invariant. Right? Now, I want you to observe and tell me that what will be the loop invariant device. What is loop invariant? Yesterday we discussed that loop invariant is something that is going to be true before you enter to the loop and after the iteration of the loop. It is going to be an observation or a statement about the loop such that that statement, that loop invariant is true. That's why you call it as invariant. It is true before entering to the loop and after the iteration of the loop also. So you should be able to guess what is the loop invariant here and tell me. Okay, so I will show you this. Then we can easily identify the loop invariant. Let us see. There is one loop that is a for loop, right? And this is how we are seeing it. So what could be the loop invariant? So this is how we are starting the loop, right? This is how we are starting the loop. So now we are just before the loop when I is 1 and j is 1, right? And after you have done one iteration, what is happening? This is there. After you have done one iteration, this is it. After you have done two iterations, this is it, right? After you have done four iterations, this is the loop. So how can I define my loop in the loop?
Ma'am, after n iterations, like n elements will be in the sorted list.
In your final output, in each, so if there are two iterations, you have two elements, first two elements which are sorted, right? Yes. So loop invariant at the beginning of the for loop of line 4 to 10. So loop invariant will always be with respect to a loop sequence. Okay, that's why the name is loop invariant. So we also have to mention about the loop. So at the beginning of the for loop of line 4 to 10, the first k minus 1 element of B. Okay, first k minus 1 element of B are the smallest k minus 1 elements from L and R in sorted order. Whatever you need is executed, right? So if you are, if you are in the, let us say, if you are in the kth iteration, okay, so you are saying that first k minus 1 element of the loop of the final output are the smallest k minus 1 element merging LNI in sorted order. That is what it means, right? So that is your loop invariant. This is how it is written.
Excuse me.
Yes.
Like there's so much of disturbance right now in your background.
What happened?
Background noise, ma'am.
You are saying again noise is there. That is what you are saying.
Yes, ma'am. It is so much today. Like, can you do something about it?
Okay, can be done. Okay, I can only try joining again. That's what I can try. Shall I do that?
Yes, ma'am.
Maybe I will also speak louder, students. Then it may be better.
Ma'am, ma'am,
Yeah.
can you know what you are using? Like, it is earphones or normal, you are putting it on speaker. Like, how you are presenting, ma'am?
Today I am using the earphones because that's how it was coming properly in all these days. Is it fine now?
It's kind of better, ma'am.
Yeah,
But
it will be fine. Okay, I will speak little louder. Probably I was not speaking louder. Okay, so I guess it will be better. What do you say, students? Hmm?
yes, ma'am.
Yeah,
Let's
it will
continue.
be. Yeah, it will be better because in between I should speak a little louder so it will work out. Okay, so that is what we were saying about the loop invariant, that at the beginning of the for loop of line 410, the first k minus elements of B are the smallest k minus 1 elements from both the array, from L and R in sorted order. All right. So let's talk about the running time. Okay. So you must have guessed by now the running time is going to be how much?
n log n.
N log n. You are saying n log n because you are first assuming that it is going to take some. N log n is the time for the whole merge, complete thing, right? Merge sort plus merging, right? You are saying merge sort plus merging. That's first for merge for merge sort means you first divided it into two arrays, right? And then you perform the merge operation. So this n log n you are saying is the time only for merge, or it is the time for the whole merge sort?
Whole merge sort.
Whole merge sort. Okay. Let
Merge
us
is
see.
n.
Merge is n. Merge is n, so running time on is going to be linear, right? Because what you are doing, you are just comparing. There is one for loop, so you are every time comparing, right? And then it is going to be linear. So you are copying either from array L or you are copying or from array R, right? But yes, you have. If you consider the whole thing, that dividing also, we will assume some time spent, some complexities involved there also. But when we talk about only merge, it is a linear time, right? So this, but now let us come back to merge sort. This is merge sort wherein we are again calling two merge sort to Ln, merge sort to R, and finally we are merging Ls and Rs, right? So then we are trying to I find out the running time of the whole merge sort. Now when you say merge sort running time, by default, the merge operation is involved in it, right? When we are saying merge sort, we are first dividing and then we are sorting the smaller portions and then we are combining the solution. So when I say merge sort as a whole, merge has to be involved in that, right? When I say merge sort, the time complexity of merge is involved in that, right? So this is how I can write the running time of merge sort, right? So we say that Tn is equal to C. C indicates a constant, some constant C, if n is small, right? So I say Tn is equal to C if n is small. Otherwise, Tn is equal to 2Tn by 2 plus Dn plus Cn otherwise. Okay, how do we get this Dn and Cn? Okay, so we call Dn is the cost of splitting the data. You have divided the data, and Cn is the cost of merging or combining the data. Okay, and we say that 2Tn by 2. Why do we say 2Tn by 2? We assume that Tn is the time when the data size is n. Now we are saying that since we may reduce it to half, right? So now we have, rather than having n, we have 2 half of n. So that's why we are making it as n Tn by 2, and there are two halves. So 2Tn by 2 plus the amount that we have spent for dividing the data and the amount that we have spent for combining the data. So you divided n, the data size was n, so that's why dn. Combining size after combination, again you will iterate over n elements, right? So it is cn, and if you are dividing it into half, okay, so it can be, if you may even divide it into n by 3 halves, for example, right? In that case, we will assume it as 3n by 3. 3 times 3n by 3. So if we assume it as half, we assume it as 2Tn by 2, right? So that is how we can calculate the running time of the merge sort that you have already calculated as n log n. Let us see how it comes, right? So cost of splitting the data we assume as linear, and cost of combining the data also we assume it to be linear. Why do we assume? Because that is how we are doing the operation. We have two arrays, we are dividing, so if there are n arrays, of course it is going to be, it directly depends on what is the size of the input, and also combining directly depends on what is the size of n, how much is the n. So that is why it is linear, right? So now running time we can also call it as Tn is equal to C if n is small, and we can combine the Dn and Cn and we can call it as 2Tn by 2 plus Cn, some constant with n. So these two linear times, dn and cn, we combine and we make this some constant c, and then this is n, right? So we can also write it as c or 2tn by 2 plus 3. And if n is very small, why do we have to see this? Why do we write this as c? Because we need a terminating condition. So we cannot always represent cn in form of, right? So for example, when there is only one
Ma'am,
element, yes.
ma'am, your voice has suddenly become too low and then the disturbance is dominating.
1 minute.
Maybe
Is it better now?
yes,
Yes.
ma'am.
Yeah, okay. Okay, let us try like this. Let us try like this. I have
Ma'am, it's
removed
not
the.
better, ma'am.
It's not better.
Yes, ma'am. Still the sound is coming, ma'am. We can't even hear your voice clearly also.
Oh God. Okay.
Ma'am,
Yes.
can you do one thing? Like, if it is possible, sometime, ma'am, if someone can, if you have another set of earphones or someone, if you can get earphones and another set of earphones, like someone else also, can we just try that one? Maybe problem with earphones or something.
Okay. Okay. I will surely try that tomorrow. Okay. 1 minute. You just wait for a minute now. Okay.
Yes, ma'am. Yes, ma'am.
Ma'am, now it is fine, ma'am. I think you removed your earphones.
All right, students. I hope it will be better. Hmm? Okay.
Yes,
Okay.
ma'am. Now it's better,
Yeah.
ma'am.
Okay. Okay. Fine. Fine. So I will change the earphones as you said. Okay. So now I have removed the earphones. Okay. So it is like this. So now let us say Tn is equal to C when n is small, and otherwise it is 2Tn by 2 plus Cn. Right? Cn is the combined effect of dividing and the combining. Both were linear, so we call it as Cn. Okay. So how exactly we get? You are actually getting O n log n, right? So how we are reaching to O n log n? Okay. So this is how we are doing it. Right? Tn is equal to C if n is small, means when it is only one element, let us say, or else 2Tn by 2 plus Cn. Right? So now let us say we have, so we are calling it as Cn here, right? So let us explore this. Tn is equal to 2Tn by 2 plus Cn, right? So suppose I have this Cn here. So the total time I can write it like this. I have Cn here, okay? And Cn is the cost, I can assume this is the cost for dividing as well as the combining. This is the cost Cn. Along with this, right? What I'm trying to do, we are dividing data into half size. So n by 2 and n by 2. So the complexity is going to be Tn by 2, Tn by 2. So I am saying that my total cost is nothing but I am just adding it Cn plus 2Tn by 2. I'm writing it like this, right? But the cost C is given when n is very small. Maybe it is 1. N is very small, maybe it is 1, right? So only one element in the array, so sorting gives me the same answer. So I will have to reduce further, right? So the next time I make this, so now when I say, so now again when I say this Tn by 2, Tn by 2, again I can write as Cn by 2 and Tn by 4, Tn by 4, right? So what I am doing is, again I am calling this Cn as Tn by 2, again I am exploring as 2Tn by 4 plus Cn by 2. So n I am replacing with n by 2. Simple. If I replace, I get it like this. So Cn by 2, Cn by 2, that gives me Cn, right? And I get here as n by Tn by 4, Tn by 4, Tn by 4, Tn by 4, right? So so I have Cn here, Cn and Tn by 2, Tn by 2. This Tn by 2 further can be written as 2Tn by 4 plus Cn by 2, right? So this is what we have written, Cn by 2 and 2Tn by 4. So this keeps on growing like this. Next time it is going to be Cn by 4, Cn by 4, Tn by 8, Tn by 8, like that it will keep on growing, right? Till how long we are going to get it? We are going to do it till we get a constant time. For example, let us say only one element here, right? So one element only in the smallest array and the complexity is going to be C, right? Like that we are going to get. So now our job is that what is the depth of this tree? Right? What is the depth of this tree? So if the depth is D, if I assume the depth is D, right? So every time what we are trying to do is, we are trying to divide it into half, right? So if depth, so this is, at this place, depth is 1. When it is Cn by 2, Cn by 2, depth is 1. At Cn by 4, the depth is 2, right? Depth 1, depth 2, like that it is going to grow, right? So now the idea is when you combine, this is nothing but Cn. This is Cn. Sum of these two is Cn. Sum of this is Cn. Sum of this is Cn, and sum of this is Cn. Right? So what is the depth? How long we are going to get? We are going to get to a depth. Suppose it is depth of D. Right? Suppose it is depth of D. So my idea is if it is depth of D, so at each level we are dividing it by 2. Right? So n divided by 2 to the power of D is going to come as 1. Right? That's what we are doing every time. So the depth D is here. If you see, we are doing n divided by 2. N divided by 2 means depth is 1 at the first level, right? So first level we did n divided by 2. D is 1, right? Next level we did n divided by 4. At this level we are doing n divided by 2. This level we did n divided by 4. So here the depth is D, means D to the power of 2. Next time we are doing 2 to the power of 3, right? What is 3? 3 is the depth, right? So 2 to the power of depth we are doing. So every time what we are doing n divided by 2 to the power of the depth, right? And at the end when I reach, then this is going to be 1. Right? So till how long we will do? Till we reach to a level wherein I have only one element in the array. Right? So this C is going to become 1. Till then we will keep on dividing, for example. Okay? So if we do that, that means the level of depth, the depth is D. So n divided by 2 to the power D is going to be 1. Right? That is what we are doing every time. Here I have n divided by this, the depth is 1, right? So 2 to the power of 1, depth is 2, 2 to the power of 2, depth is 3, 2 to the power of 3, right? So if I am saying that the depth is D, then we are going till the level 2 to the power of D. And n divided by 2 to the power of D is going to be 1, because we will not divide further, right? So this is how we get n divided by 2 to the power of D becomes 1. Now if you take log both the sides, so you get 2 to the power D is equal to n. So you get, if you take log both sides, you get like this. So you get your D becomes log of n. Log 2 base 2 is going to be 1. So you get the value of D as log n. That is why you call, whenever you divide something like this, you call it as a complexity of kind of log n. Right? So in merge sort, this log n factor is coming from the dividing part. So D becomes, the depth becomes log n. Right? So this is a depth that you are getting. Now we have to also find that at each level how much work is associated. Right? That you have seen at each level the work associated is of complexity Cn. Now if you see how many operations Cn, if you add this is Cn, this is Cn, this is Cn, every level the work is of linear complexity. Cn, 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 Cn. And how many levels you have? The levels you have is log n. Right? So it is going to be, so the work is going to be, so what is going to be the running time? At each level you have a cost of Cn and you have log n levels, right? So that is why so the complexity you call it as Cn log n. You call it as Cn log n, which is going to be O n log n, or you can also call it as theta n log n. You will be able to prove bound as less than or equal to and also greater than or equal to. So that is why you say that it is going to be theta of n log n. So the log n part comes from the dividing, and from where this Cn part comes, it comes from at each level how much work we are doing, that is dividing as well as the combining. Right? That is what is your merge sort. Was it clear, students? Was my voice audible? Is the voice audible
Yes,
now,
ma'am.
students? Okay, fine, students, fine. All right. So this is what we are going to get as merge sort. Right? So now we've actually discussed merge sort with respect to recurrence. Right? So what exactly is a recurrence? So merge sort that we saw was an example of a recurrence relation. A function that is defined with respect to itself on smaller inputs. Right? So this is important. A function that is defined with respect to itself on smaller inputs. All these are example of recurrence. For example, Tn is equal to 2Tn by 2 plus n. Tn is equal to, it is also possible. We are not saying 4tn by 4, we are saying 16tn by 4 plus n. Tn is equal to 2tn minus 1 plus n square. Right? All these are recurrences. Recurrences means the function is defined with respect to itself, but the size of the input is smaller. In this case, first case, we have made the size smaller by half. The next case, we have made the size smaller by 4, by 1/4. But we have done a multiplication with 16. In the next case, if you see, you have actually reduced the size only by 1. Then the question is it really worth? You have just reduced a size by 1. Earlier the size was n, now the size is n minus 1. Right? Those are separate things that in what kind of problems this can be applied there. You know, if running time is like this, 2tn minus 1 means n in the size was n and you are reducing the size by just by 1. These kind of problems are also there, 2tn minus 1 plus n square. Not just because we want to solve such kind of a problem. Okay, so we will find out that in what kind of application something like this will be applied. Tn is 2tn minus 1 plus n square. Okay, so all these are recurrence relations. So why are we interested in recurrences? Okay, because we want to find the computational cost of divide and conquer algorithm. So we have already seen the divide and conquer algorithms have 3 factors. One is dn for dividing, cn for combining, and atn by b is for whatever input size you have reduced. Right? Dividing, combining, and this is for solving the divided problem. Atn by b is for solving the divided problem. So a sub-problem is of size n by 2. Dn is the cost of dividing the data and Cn is the cost of recombining the sub-problem solution. Okay, so in general, why are we interested in recurrences? Is running time of most recursive algorithms can be expressed as recurrences. Right? Wherever we have a recursive kind of algorithm, we can always use recurrences there. Most of the time. Okay, so now the challenge is recurrences are often easy to define because they mimic the structure of the program. Okay, they mimic the structure of the program, but they do not directly express the computational cost. Right? So they do not directly say, the relation is given to you, but by seeing these relations, it is directly you cannot find out the computational cost here is going to be n log n, or it is going to be n square, or it is going to be n cube. We do not know, or it is going to be n square log n. Right? So that is a challenge. They do not directly express the computational cost. Okay. We want to remove self-recurrence and find a more understandable form of the function. Right? So what exactly is the idea we are going to remove? We want to remove self-recurrence, right? And then we are trying to find out more understandable form of a function so that we can finally converge to the computational cost, right? That is the idea behind the recurrence. So there are 3 approaches for this. For your recurrence relation, right? One is called a substitution method. Okay, another one is recursion tree method, and the third one is master method. All master method because you have some formula and then you can directly write the computational cost. Definitely you have to remember what is master theorem, but by now everybody would have mugged it up, right? To tell the complexity fast, right? But we will learn all the 3 approaches. Right, so master method we will be learning towards the end. Okay, so there are 3 approaches. Towards the end means towards the end of these approaches. Okay, so first is the substitution method. Okay? Substitution method is useful when you have a good guess of the solution. Okay, and then you prove that it's correct. Okay, sometimes after doing after finding out lot of complexity, after reading many problems, just by seeing the problem I know what is the answer. Like all of you knew that the merge sort algorithm was n log n, right? But that algorithm you knew using the merge sort, but if I have given you a function fn is equal to 2tn by 2 plus cn, for example. Okay, 2tn by 2 plus cn. So you will say it is n log n. Okay, because you are able to guess it. So substitution methods are used. Okay, so you have a good guess. Sometimes or the problem is not same that I have seen. Okay, something is added to it, but I can still guess it. But after guessing it, I have to prove it that it is correct. My guess is correct. Okay, so generally for proving that we are going to use the induction method, right? So I will make a guess and then I will say when my n is equal to k, it is true. So from there itself, I should find out when k becomes k plus 1, then also it is true. So if it is true means yes, my guess is correct. But if I am not able to prove, then my guess is wrong. I may have to guess something else. Okay, so that is based on the intuition, substitution method. Okay, then you have a recursion tree method. So if you don't have a good guess, then your recursion tree can help. And then you solve with the substitution method. So you do it two ways, right? So recursion tree that we drew just now for merge sort, right? N by 2, every step we did, and then you apply some of the guess. Recursion tree plus substitution method. And master method is a theorem that provides a solution for recurrences of this form. So Tn is equal to Atn by B plus Fn, then there are conditions. If Fn is like this, and if A and there is a relation between A and B like this, and Fn is like this is going to be the answer, right? That directly tells you the answer, master method. Okay, so all the three are important. All the three are important. Yes, once you learn master method, you don't want to do substitution method and recursion tree method because you directly want to apply the master method. That is all fine, right? So in substitution method, guess the form of the solution and then prove it is correct by induction. That is what we do in substitution method. So now if you have Tn is equal to Tn by 2 plus D, right? You had seen in merge sort Tn is equal to 2Tn by 2 plus Cn, right? And now we are saying Tn is equal to 2Tn by 2 plus D. Now what is D? Right? D is not involving n, so D might be a constant. 2Tn by 2 plus D. Okay, so what is happening here? Half the input, then constant amount of work. Right? So that's what it is saying. It is saying that this, if you only see this function is saying that Tn is given to me. So how I am going to find out the complexity? I am just doing Tn by 2. I am making the input size as half, and then plus D means it is some constant amount of work. So we guess it. What could be the guess? Right? So we say that it is something similar to the binary search. Right? Something, because we already know, we have some idea of binary search. Right? So rather than calling it as n log n, because it is not plus Tn here. Right? In merge sort we had 2Tn by 2 plus Tn. So this, but there is a constant amount of work. Similar to binary search, so because wherever there is n by 2, n by 2, n by 2, I am reducing. Okay, so we will say it as a logarithmic complex. So my guess is that it can be O log n. Right? So this constant we just leave, we don't consider for it. Okay, so we say that okay, O log n could be the complex. So now I must prove it. Right? So what I have to prove? I have to prove that Tn is equal to Tn by 2 plus D should be O of log n base 2. Should be O of log n base 2. Right? So what is the idea? The idea is we might prove it by induction. Right? So we assume that it is true for smaller value of k when k is less than n. When k is less than n, it is true. Okay, and then we prove that it is true for the current Tn also. So in general, so far, whatever math we have learned, what we say is we assume it that it is true for some value of k, and then we try to prove it that it is true for the value k plus 1 also. Here we can prove it by, we assume that it is true for smaller k, some value of k, wherein k is less than n. Okay, and then we say that it is true for the current Tn also. That is another way to prove. So in your algorithm analysis, the proof by induction, exactly we do not say that it is true for k, so it is true for k plus 1. We say that it is true for some tk where k is less than n, and then we say that okay, because from there we will derive that it is true for the current Tn as well. Okay, so for example, so Tn is equal to Tn by 2 plus d. We assume, now this is what we are assuming. We are assuming that Tk is equal to O log k base 2. right? So I'm replacing, so this is what was our guess, right? That it is O log n. So we say that Tk is going to be O log k base 2 for all k is less than n. For smaller values of k, when k is less than n, we are saying that, assume that it is true. So now what we need to do is we need to prove that because this is true, it is true for Tn is equal to O log. It is true for n also. So when I replace k with n, then also it should be true. Right? That is what we need to prove now. So little bit of math we may have to apply, right? So from our assumption, okay, from our assumption, what is going to happen? From my assumption, Tn by 2 is equal to O log n by 2 base 2. Right? Because what was the assumption? The assumption was Tk is equal to O log k for all k is less than n. So from that assumption itself, we will get that T n by 2. Why did I do n by 2? Because I want to introduce the term n now. And n by 2 is obviously less than n. Right? So we assume that Tk is equal to O log k. So from that assumption, we will say that Tn by 2 is equal to O log k, O log n by 2 base 2. So now if we assume this, we will go back to the definition. Right? What is the definition? The definition is Fn is equal to O of Cn if there exists positive constant C and N such that 0 is less than equal to Fn is less than equal to C of Gn for all n is greater than equal to Ng. Right? Now if I am saying that this Fn is equal to O of Gn, I should be able to have this equation correct. That is Fn is less than equal to C of Gn. Right? So from that, what do I get? So this is the definition of big O. So this is what I get. Fn. So now if I am saying Fn is equal to O of Gn, so Fn is less than or equal to C of Gn. Simple. I have just put it here because we assume this. We assume this is correct. So firstly, we started with we assume that it is correct for smaller values which are less than n. K is less than n. It is correct. Okay. So when we assume this, we said that it becomes O log k base 2. Then we said that, okay, if that is the case, let me take k as n by 2. So T n by 2 is O log n by 2 base 2. Because n by 2 is less than n. And we have said for all the values of less than n, it is true. Now once we have proved this, once we are saying this, so Tn is equal to O of Gn. That means Fn is equal to O of Gn means Fn is less than or equal to C of Gn. C of Gn. So now once I get this, right? So now how do we now prove? But exactly what we wanted to prove was we wanted to prove that Tn is equal to O log n. Right? And what is given to us is Tn by 2 is less than equal to C log n by 2 base 2. Right? So now what we can do that. Okay. So now to prove that, Tn is equal to O log n, we need to identify the appropriate constant. Okay. We need to identify the appropriate constant. So some constant C, I should find out some constant C such that Tn is equal to C log n. So basically what we are saying is we actually want to prove Tn is equal to O log n, right? So from this equation, we are actually getting Tn. So basically what we are getting is by our assumption, we are getting Tn by 2 is less than equal to C log n by 2. Right? But what we are trying to prove, we have to prove that Tn is equal to O log n. Now to prove Tn is equal to O log n, what we require is we need to have appropriate constant such that Tn is less than equal to C log n. Right? We need to find out the appropriate constant C which says that Tn is less than or equal to C log n. Okay? But what is given to us is, this is what is given, Tn by 2 is less than equal to C log n by 2. What is given? So Tn is equal to Tn by 2 plus D. Right? Tn is equal to Tn by 2 plus D. Why did we do? This is what is given to us. Tn is equal to Tn by 2 plus D was given to us as the original equation. No? Then only we made a guess. Right? Tn is equal to Tn by 2 was given to us. For this only we made the assumption that it is right? So from our inductive hypothesis, I can write it as Tn by 2 plus d was given to me, right? Tn is equal to Tn by 2 plus d was given to me originally. And I found out that Tn by 2 is less than or equal to C log n by 2 plus d. Right? How did I write? Because we had come to a proof that from this we had come to know that Tn by 2 is less than equal to C log less than C log n by 2 plus from our inductive hypothesis. If that hypothesis is correct, then Tn should be like this, right? I can explode this expression as C log n base 2 minus C log 2 base 2 plus D, right? Simple now. Now, C log 2 base 2 is C. So this is C log n base 2 minus C plus D. Both of them are constant now, right? So since both of them are constant, I can call them as residual, right? And I can say that this is less than or equal to C log n base 2, okay? If C is greater than equal to D, right? So I can ignore these terms. I can call them as, yeah? Yes?
Am I audible, ma'am?
Yeah, you are audible.
So your voice has become very low and then disturbance is got very increased. Can we at least continue the class tomorrow, ma'am?
So you want me to stop the class now?
Like we are not. I don't know about others, but then I'm not able to focus also like from so long. It's just so much disturbance. And when I'm increasing the sound, the disturbance only is dominating. And when I'm decreasing, your voice is almost not audible. Like it is very low.
Okay. What can be
Ma'am,
done?
I think there is some issue with the drivers. Uh, we will check, ma'am. I will also see about what can be done.
Okay. Okay. What about others, students?
For us also, it's like that only, ma'am.
Same.
There's a lot of disturbance.
Good. Okay then. Okay, we'll continue tomorrow then. Let me try to fix it up. Continue tomorrow then, students. All right. But did you understand? The math involved there in whatever we are doing.
Actually, last 5 minutes was we couldn't understand anything. The voice is too feeble.
Okay. Okay. All right. So maybe I will change the place from tomorrow. Maybe then it may work.
Ma'am, can we try one thing? If you can end the recording, we can end the class. Those who want to leave can leave, and then we can experiment few things.
Okay.
End recording, ma'am. Okay. I will call
End. It will end automatically.
Yeah, but then meeting also will end. No?
Okay.
It's okay, ma'am. I'll call personally, ma'am. Like directly.